Welcome to engineering physics. So in the previous classes we have learned about what are mechanical properties, why do we study mechanical properties of solids, and then we have also seen what is engineering stress and what is engineering strain. So and we have also seen various types of stresses that can be applied, such as tension, compressive stress, then shear stress, and finally torsional stress. Before going to today's topic, I would like to remind you what we have learned in the yesterday's class. So first of all, we have learned about most important mechanical properties. They are stiffness. The second one is strength. Third one is hardness, and the fourth one is ductility. So these are the four important mechanical properties of solids. So stiffness, resistance to plastic deformation, resistance to plastic deformation. So strength is the maximum stress that a material can withstand, maximum stress that a solid can withstand. Hardness is resistance to the localized plastic deformation due to indentation or abrasion. Finally, ductility is the measure of the degree of the plastic deformation. So these are the four important mechanical properties of solids which we have learned in the previous classes. We have seen about stress or engineering stress. It is represented by sigma. So stress is nothing but force per unit area, or you can also simply define it is a ratio of force to the cross sectional area of the material. Otherwise you can also define like this: the amount of force that is applied per unit cross sectional area is known as stress or engineering stress. So the units are megapascal or gigapascal. So mega means 10 power 6 Pascal, giga means 10 power 9 Pascal. Then we have seen about strain. It is represented by epsilon. So it is nothing but the change in the length divided by original length. So strain is nothing but, because in the numerator we have the length, denominator also we have the length, so it is a dimensional quantity. It has no dimensions, it has no dimensions. So strain is nothing but the change in the length divided by original length of the material or solid. So this is what we have learned in yesterday's class. In addition, we have also seen various types of stresses. So tensile stress, compressive stress, shear stress, and then torsional stress. So this is what we have learned in the previous classes in brief. Now we are going to learn about Hooke's law. So this Hooke's law gives the relation between stress and strain. In the previous classes we have learned about what is stress and what is strain, and various types of stresses such as tensile stress, compressive stress, shear stress, and torsional stress. Now we are going to see how the stress is related to the strain, and that relation will be given by the Hooke's law. Before going to that, let us have a simple example. Suppose if you see this diagram, we have a spring. When we apply some load, say for example 5 kg. So because of this load, a force mg will be acting downwards. Because of that, the spring stretches a distance of x when we apply 5 kgs. Suppose if I apply 10 kgs, 5 kgs, you can see here 5 kg plus 5 kg. If I apply 10 kg, what happens is the elongation of the spring becomes double. So x becomes 2x. So when I apply 5 kg, that means 15 kg, the elongation becomes 3 times when we apply 5 kg. So when we apply 20 kg, the elongation of the spring becomes 4 times when we apply a load of 5 kg. So from this you can see, as the stress increases, strain is also increases. Strain increases as the stress increases. So from this we can have the relation between stress and strain. So that relation is given by scientist called Hooks. So stress is directly proportional to the strain. Stress is directly proportional to the strains. So as the load increases, the change in the length of the spring increases. So stress is directly proportional to the strain. So this is the relation given by the Hooks, and this is called Hooks law. But there is a condition for this law. So this stress is directly proportional to strain only in the elastic limit. Only in the elastic limit. So we can define the Hooks law as within the elastic limit, stress is directly proportional to strain. So this is called Hooks law. So let us see once again what is Hooks law. So Hooks law gives the relationship between stress and strain within the elastic limit. So Hooks law can be defined as, so within the elastic limit, stress is directly proportional to the strain. Now suppose if I plot a graph between stress and strain for a given material, that means suppose if I plot the graph here, so I apply a stress of load of 5 kg, 10 kg, 15 kg and 20 kg. So if I apply and I have a strain in the spring, when I apply 5 kg, 10 kg, 10 kg, 15 kg and 20 kg. So if I plot a graph by taking stress along y-axis and strain along x-axis, then the graph will be like this. So this is called stress strain curve. So this graph is shown here for materials within the elastic limit. So within the elastic limit, stress is directly proportional to strain. So suppose you can see here, as the stress increases, strain is also increases continuously. So what is the significance of this stress strain curve? Now the Hooks law is sigma is proportional to epsilon, that is stress is directly proportional to strain. Now sigma is equal to E epsilon. So where E is modulus of elasticity, modulus of elasticity. The constant of proportionality E is called modulus of elasticity, that is constant for a given material. Now it is also called as Young's modulus. This is also called as Young's modulus. Now here we have considered tensile stress. So when we apply tensile stress on a particular material, so the stress is directly proportional to strain. So we have this relation sigma is equal to E epsilon, where E is called modulus of elasticity. It is also called Young's modulus. From now here we can have E is equal to sigma by E. E is equal to sigma by E. Now let us see what is the significance of this stress strain curve, or what is the significance of this Young's modulus or modulus of elasticity. Otherwise, what is the mechanical property which we can obtain from this stress strain curve? Now let us see the significance of this stress strain curve. So you can see here, this is called stress strain curve. Strain is along the x-axis and stress is along the y-axis. According to the Hooke's law, the stress is directly proportional to strain. So sigma is equal to E epsilon, where E is called constant of proportionality. It is called modulus of elasticity. It is also called as Young's modulus. So we have the formula E is equal to sigma by epsilon. Now let us see what is the significance of this stress strain curve. Now if you see here, the mechanical property that we obtain from this stress strain curve is stiffness. Stiffness. So the modulus of elasticity, it is thought of as stiffness of a material. That means if I found modulus of elasticity of a particular material, then that can be equal, that is nothing but I have found stiffness of that particular material. So this modulus of elasticity E it has a long range. That means it is different for different materials. Say for example, if I take E is equal to 45 gigapascal for magnesium, and it is E is equal to 407 gigapascal for tungsten. Like that, we have various types of metals, and each metal will have a particular value of Young's modulus E. So the least value we can obtain for a metal is magnesium metal. So its Young's modulus is 45 gigapascal, whereas we have a tungsten which has very high modulus of elasticity or Young's modulus. So E is equal to 407 gigapascal for tungsten. So by comparing these two values of Young's modulus, you can say tungsten is stiffer than magnesium. So tungsten is stiffer than magnesium. That means it will not undergo a considerable plastic deformation. Let us see this by using the formula. So we have Young's modulus E is equal to sigma by epsilon. Now if you see here, if I take magnesium and tungsten, if I apply a force of, say for example 30 megapascal, otherwise okay, and 30 megapascal for both, then from the formula, so what is the stiffness of the material? So E is equal to 45 gigapascal is equal to 405 gigapascal. So let us supply some x gigapascals. Suppose if I apply a stress of some x gigapascal for magnesium and tungsten, so the Young's modulus of magnesium is 45, whereas Young's modulus of tungsten is 407 gigapascal. That means sigma is same for both the materials, but E is different. So what does it mean? So the strain is different for these two different materials. So E high means the strain of the material is less. If the stiffness of the material is high or the modulus of elasticity of the material is high, that means the strain experienced by the material is low. So that is the meaning of this thing. Okay. So Young's modulus is E is equal to sigma by epsilon. So we have two examples, magnesium and tungsten. Magnesium is having very less Young's modulus or modulus of elasticity, whereas tungsten is having very high modulus of elasticity, that is 407 gigapascal. Now let us move on to the next point. How do we calculate E from the graph? So the modulus of elasticity is equal to sigma by epsilon. The sigma by epsilon is nothing but the slope of the curve, slope of this stress strain curve. So what we have seen about this stress strain curve up to now is, from Hooke's law, within the elastic limit stress is directly proportional to the strain. And what is the significance of this stress strain curve, and what is the mechanical property that we will obtain from the stress strain curve is the stiffness of the particular material. Stiffness of the particular material is equal to the Young's modulus of that particular material. So Young's modulus can be obtained from the slope of this stress strain curve. So E is equal to sigma by epsilon. This Young's modulus is different for different materials. That means if you take two materials like magnesium and tungsten, if you apply the same load, then the E is the E you get for magnesium is 45 gigapascal, whereas E you get for tungsten is 405 gigapascal. It is because these two materials have different strains. That means magnesium is softer material, whereas tungsten is very hard material, okay, stiff material. So that means the strain experienced by the tungsten is very less compared to the magnesium. So because of this property, tungsten has been used in many applications like filaments and glass cutters is the important application. In cutting tools, tungsten has been used. So because of its high stiffness, it can be used after the diamond is used for the cutting of the materials. Next to the diamond is tungsten, which is the hardest hard material. So this is about stress strain curve for metals in the elastic region. This is valid for metals only. This is valid for metals and in the elastic limit. So these are the two conditions. One is this stress strain curve is for metals, and the second one is it is valid in the elastic limit. So now let us see how the stress strain curve will be for materials like polymers or cast iron. So this cast iron is an iron, but it has relatively lower melting point compared to the iron. So they will exhibit a particular kind of stress strain curve. The stress strain curve which we have seen in the previous slide is a linear curve. That means if stress increases, then strain immediately increases. If you remove the stress, then strain will also be removed. So this type of deformation is called elastic deformation. Or you can call it as elasticity. That means the moment you remove the stress or load, it regains its shape back. So elastic deformation is also called as non-permanent deformation. Non-permanent deformation. Okay. So for most of the metals the curve is linear, but for other metals if the curve is not linear, if the curve is like this, then how do we measure modulus of elasticity or stiffness of that particular material is? So you can have two methods. One you can take tangent modulus, or you can take secant modulus. So if this is the curve, then if you draw a tangent here, then the slope of that tangent is equal to sigma e by delta e by delta epsilon. So that is nothing but the slope of this tangent. So you can find by using this tangent modulus, or you can also find the stiffness of this polymers or cast iron or cement by using the secant modulus also. That means, so you draw a curve from the origin. Okay. So this line touches the stress strain curve at a particular point here. So that is the sigma, and you take slope for this curve. This is delta E delta sigma by delta epsilon. So that can also be taken for determination of the Young's modulus of these materials. Now, why some materials are stiffer and why some materials are softer? In other words, why some of the materials are having high modulus of elasticity, why some of the materials are having low modulus of elasticity. Why some materials have very low Young's modulus, and why some of the materials are having very high Young's modulus. So this is because of the reason behind the low values of E and high values of E for other materials is due to the bonding between the atoms of the solid. Suppose if the bond is very strong, then we need to apply more force to break it. If the bond strength is low, then we need not apply huge force to break the bond. So what happens here is, so if the E is high, that means the bond strength of the material is very high. So most of the ceramics E value is very high. Similarly for metals also, the modulus of elasticity is high. So whereas if you take polymers, rubbers, okay, so cast iron, cement, so they have low value of E because the bonding or the bond strength between the atoms of those particular solids is not strong. The bond is not strong. So the Young's modulus of those materials is low. Now we can also see now let us see so we have we have a force versus equilibrium distance or distance curve. So this R represents the distance between the two atoms of the solid and F is the force. So the curve is, suppose I am writing this curve for two different materials. Suppose if I take and I can say which of these materials is stiffer, or which of these two materials, let us say this is A and this is B, and simply by looking at this curve I can say B is stiffer than A. So because as I told you, the Young's modulus depends upon the bonding energy between the atoms. So here if you see, if I take the slope, so this will be dF by dr. So this is the slope. So this is also dF by dr. dF by dr for A, dF by dr for B. So Young's modulus is proportional to dF by dr. If the force between the two atoms is strong, then we need to apply more force. That means the material is strong. That means the stiffness of the material is very high. So automatically the material will be having high Young's modulus or modulus of elasticity. So other way to find the stiffness of the material is by looking at the force versus interatomic distance curve. So if the curve is more steeper, then you can say that the material is more stiffer. Okay, so this is about stress strain curve of a metals, and we have also seen how will be the stress strain curve for polymers and grey cast iron. So and we have also learned from the stress strain curve how do we measure the modulus of elasticity, what is the significance of this modulus of elasticity, that is, so you can determine the stiffness of the material by using the Young's modulus. So Young's modulus is equal to the stiffness of the material. So we have seen Young's modulus for different materials such as magnesium and tungsten. So for magnesium, the Young's modulus is 45 gigapascal, and for tungsten it is 407 gigapascal. So this is because the bonding between the atoms of the tungsten is very strong, whereas the bonding between atoms of the magnesium solid is relatively weak compared to the tungsten. So we can also determine stiffness of the material, or relatively we can say which of the materials, which suppose if I take one material or more two material or more than two materials, then if I want to say which of these materials have high Young's modulus or high stiffness, I can do that simply by looking at force versus interatomic distance curve of those materials, because Young's modulus of a material is directly proportional to the slope of that particular force versus interatomic distance curve. So this is about stress strain curve of different materials within the elastic limit, and we have also seen elastic deformation. That means the moment you remove the force, the material gets back its original shape. You can also term it as a elasticity. And we have also another one called plasticity. That means if you apply the force, then the material undergo some plastic deformation, that means strain will be induced, but the moment you remove the force, it will not regain its shape, original shape back. So that is called plasticity. So here we have seen about elastic deformation. Okay. So now this is all about the stress strain curve. So here I have put a slide which represents Young's modulus, Poisson ratio. Now we are going to see what is Poisson ratio, okay, for different metals, ceramics, okay, and polymers. So you can see here for metals, tungsten is having 59 gigapascal, whereas magnesium is having 45 gigapascal. So other metals like steel, nickel, titanium, copper, you can see here how the Young's modulus is varying for them. Similarly, you can see some of the ceramic materials which we have been used in most of the mechanical engineering applications, say for example in engines, in mechanical engines. So those materials should withstand very high temperatures, that means around 2000 degrees centigrade, where alumina or zirconium oxide have been used. So you can see here aluminum oxide is having 393 gigapascal, silicon carbide, silicon nitride. See, most of the ceramics have Young's modulus approximately here beyond 150. Okay, so mullite it has 145. So except these three, so all of them having very high Young's modulus. Whereas if you see polymers, so we don't have a particular value for polymers. It is ranging from 2.76 to 4.83, because we cannot measure Young's modulus as we measure it for ceramics and metal alloys. Okay. So now we have seen stress strain curve. So sigma, that is stress along the y-axis, strain along the x-axis. So this is a straight line, this is a linear curve. So according to the Hooke's law, as the stress increases, so strain produced in the material will also increases within the elastic limit. So the condition is within the elastic limit. Within the elastic limit. So now if I take a metal, so for example you take a copper wire, and if we hammer it, then what happens is, so its dimensions will change. It becomes thinner, thinner, thinner. Suppose if you apply very little force, then it experiences plastic deformation, which we cannot see with our naked eye, but it regains its shape back. But if you apply enough force, what happens is its dimensions will change. Even though you remove the force, it will not regain its shape back. That means it exhibits plastic deformation. So we have two types of deformations. So one is elastic deformation, and the second one is plastic deformation. What we have seen up to now in the previous discussion is the stress strain curve in the elastic region. So that means elastic deformation. So now we are going to see what happens if the stress is increased beyond a particular value, or what happens beyond the elastic limit, how this stress and strain will be related to each other. So there is if I take a material, it exhibits both. First of all, it exhibits elastic deformation. So after that, it exhibits plastic deformation. So there is a transition from elastic deformation to plastic deformation. So there is a transition. So the whole curve for a particular material will be like this. So original stress strain curve for a particular material or metal will be like this. So this is the complete stress strain curve for a given metal. So but in the previous discussion we have seen only up to here, that is within the elastic limit. But beyond the elastic limit, the stress strain curve will be like this. That means Hooke's law is not applicable. That means stress is not directly proportional to strain from here to here. So now let us see what happens in this region of plastic deformation. Now let us see right. So there is a transition from elastic deformation to plastic deformation, or from elasticity to plasticity. So the point at which the material changes from elastic deformation to plastic deformation is called yield strength. Is called yield strength of that particular material. So sigma y is nothing but yield strength. Sigma y is nothing but yield strength. So what is yield strength? The definition which we should learn is yield strength. What is the yield strength is, so the stress value at which the material changes from, or material undergoes from elastic deformation to plastic deformation. So yield strength is nothing but, this is the stress value at which the material exhibit plastic deformation. So sigma y can define as the stress at which the material goes from elastic deformation to plastic deformation. So this is a transition point. That means we have some transition stress value at which the material changes from elasticity to plasticity, or elastic deformation to plastic deformation. So that transition stress value is known as yield strength. So if you see here, so this is the maximum stress sigma Ts. This is the maximum stress value that a material can withstand. So that is known as tensile strength sigma Ts, or ultimate tensile stress. It is also called as UTS, ultimate tensile stress. Ultimate tensile stress. So that is nothing but, so this is the point where plastic deformation starts. So if you apply more force, then the deformation or the strain will also increases at a rapid rate, okay, and we have a maximum stress value of the material, so beyond which the curve changes. So what is happening here is, as the stress decreases, strain increases. So this is the meaning of this curve from here to here. So we have two regions. So one is elastic region. So this is called elastic region. Let us indicate with ER, and this is called plastic region. So after this, what happens is, even if you don't apply the force, the material undergoes a huge strain and ultimately undergoes a strain. This is called necking. This process is called necking. So necking is the point where plastic deformation, more plastic deformation occurs. So the finally fracture occurs. That means the material breaks into two pieces. So for this, you just take a bubble gum, okay. So if you apply very slight force and leave it, then it regains its shape back. It's not a perfect example, but you can try it. So if you apply a little force and leave it, then it goes back to its original shape. So as you apply more force, there is a region transition stress, if you apply more than that one, then plastic deformation starts. After that, so it will not regains its shape back. So as you apply more force, so it stretches. Okay, so after a particular stress you need not apply any force. So if you keep like this, by itself it becomes two pieces, it breaks into two pieces. So that is that process when even if you don't apply any force, the plastic deformation or the elongation increases is called necking. So ultimately fracture, that means the material breaks into two pieces. This is the whole stress strain curve for a material, so which includes both elastic deformation as well as plastic deformation. So from this, what you have to remember is, so one is yield strength, the important definitions are yield strength, and then ultimate tensile strength, and then third one is necking, and the fourth one is fracture. So these are the four important definitions we must learn. So here, as I told you, so this is a stress strain curve. Yield strength is nothing but the strength at which, or the stress level at which the material changes from elastic deformation to plastic deformation. So the transition stress value at which the material undergoes plastic deformation. So how to determine this yield strength practically? So we apply some force, we measure the strain, and so for stress and strain values we plot a graph. If the graph is like this, so to determine the yield strength, what we do is, at a strain value equal to 0.002. So at a strain value equal to 0.002, we draw a parallel line to the stress strain curve. We draw a parallel line to the stress strain curve. Okay, so this line cut the stress strain curve at a particular point. So the stress value corresponding to the intersection of the line which we draw and the stress strain curve is called yield strength. So that is how yield strength of a material or metal can be determined. Okay. Then you can see here the whole curve we have discussed here. Okay. So in this curve, so we have yield strength, okay, tensile strength. So sigma is equal to Young's modulus is equal to sigma by epsilon. So this is the elastic region and this is the plastic region. Okay, so this is the necking and this is the fracture. So these are the important definitions. If you want, you can note down. So the yield strength, the load at the yield point divided by the initial cross sectional area. Otherwise you can simply call, so at the yield point it is the transition stress value at which material changes from elastic deformation to plastic deformation. Okay, ultimate tensile strength or ultimate tensile strength, it is the maximum engineering stress which a material can withstand. So necking is nothing but the concentration of plastic deformation in a localized region of sample. So fracture is, so at a particular stress value the material breaks into two pieces, that is called fracture. So this is about that is about the stress strain curve. Now let us see what is Poisson's ratio. So now if you see this diagram here, we have a wire of length L0 and cross sectional diameter of D. Then if I apply a tensile force, what happens is there is a change in the length, that means length increases whereas diameter decreases. So diameter decreases. So we have a stress along the axis, that is called linear stress. So we have seen up to now, what we have seen is linear stress. Okay. So this linear stress is nothing but L minus, sorry. So now it is, let us see about the Poisson ratio. So the moment we apply tensile load, the material undergoes a deformation, that means the strain will be induced in the material. Suppose if I take a wire of length L0 and diameter D0, suppose L0 is length, D0 is diameter. So what happens is we have two types of strains. So one strain is along the axis. So along the axis means this is. So another one is perpendicular to the axis. So along the axis, the strain which is along the axis is called linear strain. Another one is called lateral strain. So the Poisson ratio is nothing but lateral strain by linear strain. So the Poisson ratio is nothing but lateral strain divided by linear strain. So that means, so we have changes in the length the moment we apply tensile load. So the strain is L minus L0 by L0. So this is linear strain. So lateral strain is, it is nothing but D minus D0 by D0. So this is the lateral strain. That means there is change in the length as well as change in the cross sectional area. So the ratio of these two strains is given by is equal to Poisson ratio. So the Poisson ratio, it is a number. Okay. So it is nothing but the ratio of the lateral strain to the linear strain. So the Poisson ratio value is ranging from 0.2 to 0.4, at the most 0.5. So this is the range of the Poisson ratio value. So from this, what we can observe is the linear strain is always greater than the lateral strain. So you see, so 0.2 to 0.4 means, so the denominator value is always greater than the numerator value. So the linear strain is always greater than the lateral strain. That means the change in the length compared to the area of the wire under the tensile stress is always greater. Okay. So this is about the Poisson ratio. So up to now we have seen about stress strain curve, Before that we have seen what is Hooke's law, how a Hooke's law gives us a relationship between stress and strain, and we have seen what is Young's modulus, how do we determine Young's modulus, and then we have learned about significance of Young's modulus. So significance of Young's modulus is it gives stiffness of the material. Okay, so we have seen stiffness values for different materials, and then we have seen complete stress strain curve for a given metal or material. Okay, so we have learned about various definitions like what is yield strength, what is ultimate strength, what is necking, and what is fracture. These are the four important definitions related to the stress strain behavior of solids. Particularly the curve which we have seen is for metals. Now we are going to see about the failure of metals, failures. Failures of metals, because in most of the applications we use metals compared to particularly in mechanical engineering applications. So most of the materials used are metals. So ceramics and polymers, they are very rarely used in the mechanical engineering applications. So it is necessary for us to learn about these engineering applications of metals, particularly this topic called failures of metals. So failure of a metal or a solid is most undesirable thing. It is the most undesirable thing, because failure of metal causes economical loss, resource loss, human lives will be lost. So because of the failures we have these three severe losses. Suppose if you are moving on a bike, if the axle is broken, then what happens? So economically you will lose. So the resources will be lost. At the same time, the human lives also lost. Sometimes people may die. Sometimes people may lose their lives. Okay. So failures of metals is a most undesirable thing. So in these failures we are going to see about three types of failures. So one is fracture failure, second one is fatigue failure, third one is creep. In the fracture, again we have brittle fracture, ductile fracture. So we are going to see about these three failures. So first one is fracture. So in the fracture we have brittle fracture and ductile fracture also. Secondly, so we are going to see fatigue fracture. So and finally we are going to see about creep. It is another type of failure of metal. Okay. So now let us see what is fracture. So if you see this diagram, so you can see shipwreck. A shipwreck. So because of this shipwreck, what happens? The amount that is spent to build the ship is lost without fulfilling its purpose, and then some of the human who are working in the ship might have injured or lost their lives. If there is some material which has been transported by the ship might fall into the water, and that may be lost. So because of the failure, we have this kind of losses. Resources will be lost, human lives will be lost. At the same time, there is a huge economic loss also. Now let us see about what is fracture. So fracture is nothing but it is simply breaking of a material into two pieces in response to the applied stress level at temperatures that are low relative to the melting point of the material. That means, suppose if I take a material, I will keep it at a temperature less than its melting point, and I apply some stress, then that material will be broken into two pieces. So fracture is nothing but simple definition. It is breaking of material into two pieces at a stress level in response to the applied stress at a temperatures lower than the melting point. As I told you, so we have two types of fractures. One is brittle fracture and the other one is ductile fracture. So here we are going to see about so let us see what is ductile fracture. Let us see what is ductile fracture. So fracture is nothing but breaking a material into two pieces in response to applied stress below its melting temperature. Below its melting temperature. Below its melting temperature. Now, ductile fracture. We have ductility. We have learned about ductility in the previous classes. So ductility is nothing but measure of the degree of plastic deformation. Measure of the degree of plastic deformation is called ductility. So it is quantitatively represented as percentage of elongation. So ductility can be written as, suppose, L minus L naught by L naught into 100. So the percentage of elongation is nothing but ductility. So you can take in terms of area also. Now ductile fracture is if the material exhibits a considerable plastic deformation before its fracture, then that kind of fracture is called ductile fracture. If the material does not exhibit a sufficient plastic deformation before its failure or fracture, then it is called plastic deformation. So in the case of ductile fracture, there is a considerable plastic deformation of the material, whereas in the case of brittle fracture, so there won't be any considerable plastic deformation. For example, if you take a wire, copper wire or anything, copper wire and glass, if you take two examples, so if you take copper wire and a glass, you take the hammer and hit both of them. So the copper wire, as you hit with the, let us suppose this is copper wire, as you hit, so suppose if this place, at this place it becomes like this, as increases it stretches more. So at a particular point it breaks into two pieces. So but in the case of glass, so the moment you hit here, if the sufficient force is applied, it will breaks into two pieces. There won't be any plastic, it will not stretch, it will not stretch anymore, it will not stretch at all. So the moment you apply force, if it is sufficient, then it breaks into two pieces. So this is ductile, this is brittle. So copper is a metal, glass is a ceramic. So ductile fracture is observed in metals, whereas this brittle fracture is observed in ceramics, because ceramics are brittle in nature, they won't exhibit sufficient or considerable plastic deformation, whereas metals are ductile in nature, so they will exhibit significant plastic deformation before they breaks into two pieces. Now so you can see here these two pictures. So this is called cup and cone fracture in aluminium, and this is brittle fracture in mild steel. So you can see here, so there is no any plastic deformation, but here you can see the ends of these two pieces which are breaks into two. Okay, so this one end is, it is like a cup, it is like a cone, and this is like a cup. So that is called cup and cone fracture. So brittle fracture is like that. So they will suddenly breaks into two pieces like that. So in a highly ductile material, the fracture will be like this. So initially the material will be like this. As you apply force, so it stretches, so it becomes like this. So the two pieces, after breaking into two pieces, their edges will be like this. They are very sharp. That means what you see here is the area at the edges of the two pieces becomes 0. So it is almost 0 area. So that is the case in a brittle fracture. Whereas ductile fracture. Whereas if you see the brittle fracture, so we don't have any plastic deformation. They will simply breaking into two pieces like that. So for any fracture, so first of all there should be two things are there. So one is crack formation, second one is crack propagation. Crack formation and crack propagation. So what happens is, the moment you apply force, so the material will be strained. Then if you apply more force, so the crack will be formed. So as you apply more force, the crack will be, it is increases, that means propagates. Here we have small cavities all together become a big cavity crack. Okay. So as you increase the force, what happens is this crack propagates. So it is propagating like this. So ultimately we will have a final fracture. So this is the process how a fracture will be occurs. So two things are, one is crack formation and the other one is crack propagation. So first of all, the moment you apply force, the material will be strained. If you apply more force, what happens is a small cavities or cracks will be formed. As we increase the force, all the small cavities join together and forms a bigger cavity. If we still increase the force, what happens is this cracks starts propagating in the material, that means extending in the material. So because of this extension of the crack or propagation of the crack, the material will be broken into two pieces. So this is about the fracture of a metal, fracture of the metals. Okay. So in the ductile fracture, what happens is in a brittle fracture, what happens is, so the crack propagation and crack formation and propagation, they will be done at a very faster rate, okay. So this is the case how a fracture will occur in a ductile material. So stages of ductile fracture, whereas we don't have this kind of process in the brittle fracture. So it occurs very suddenly. So fatigue is a failure that occurs due to the fluctuating stresses, and this fatigue failure occurs at a stress value very much lower than the material's tensile strength. So the strength of the material is nothing but the maximum stress that can withstand by a material, that means at which stress value it breaks into pieces. But this fatigue failure, it occurs at a stress value lower than the strength of the material. As I told you, so it is 90% of the failures are nothing but fatigue failures. Another thing is this fatigue failure, it is very dangerous one. It occurs very suddenly without any warning. So another point is, even in a ductile materials, this fatigue failure occurs. The fatigue failure will be brittle in nature. Say for example, if you take a iron wire, so if you hammer it, what happens is it stretches. After it stretches, so after stretching, you can simply break it into two pieces. That means it becomes brittle. As we apply more force, it becomes brittle and breaks into two pieces. So even in a ductile materials, the fatigue failure will be brittle in nature. See, so here for fatigue fracture, we have a curve called SN curve, where S is SN curve, where S is stress value and N is number of cycles. So this SN curve gives us the information about the fatigue failure. So what happens is, a stress value which is equal to to find the fatigue failure of the material, a stress value which is equal to 2/3 of its tensile strength will be applied on the material. 2/3 of the stress value will be applied many times. That means number of cycles, and they will count for how many cycles the fatigue failure will be occurring. So that is how experimentally a fatigue failure will be determined. So a 2/3 of its tensile strength or tensile stress will be applied on the materials number of times. So at a particular or after a particular number of cycles, the material breaks into two pieces. So that gives the fatigue failure of the material. Suppose if we take, it is different for different materials. Suppose if I take ferrous materials, the curve will be like this. So for ferrous materials, the curve is like this. Suppose if the strength is high or stress is high, S is nothing but the stress. It can also be called as stress amplitude. So if the stress is high, then the fatigue fracture will occur at a less number of cycles. Suppose if I decrease the stress value, then what happens is, you can see here the number of cycles increases. If I still reduce the stress value, then the number of cycles goes on increases. Suppose there is a stress value at which or beyond or below that stress value, there is no fracture, fatigue fracture occurs. This limit is called fatigue limit. That limit is called fatigue limit. So fatigue limit is nothing but the stress value below which fatigue failure will not occur. So that stress value is called fatigue limit. So if you apply stress value below this, there won't be fatigue failure. That means, suppose if you apply stress value below this in this range, even if 10 power 10 cycles or 10 power 100 cycles you apply, there won't be any fatigue failure. So this is the curve for ferrous materials. For ferrous materials it will be like this. So for non-ferrous materials the fatigue failure curve will be like this. So here we have two definitions, one is fatigue strength, another one is fatigue life. So fatigue strength is nothing but, so here N1 will be constant, that is number of cycles will be constant, okay. So then I will determine the amount of stress that should be applied for the fracture failure. So that's why it is called fatigue strength at N1 cycles. So similarly fatigue life at stress S1. So here I will keep strength constant or stress constant, so and I will measure number of cycles that are required for fatigue fracture of the material. So number of cycles required for fatigue failure is called fatigue life. Similarly, so if we keep N1 constant and if you measure the strength at which fatigue failure occurs is called fatigue strength, okay. So this is about the fatigue fracture. So the total number of cycles required to bring about final fracture is called fatigue life, whereas the maximum stress withstand by a material undergoing repeated cycle of loading before fractures. Only thing is the stress that can be applied before the fracture at a constant N value is called fatigue strength. Similarly, fatigue life is the number of cycles that can be applied at a constant stress value. So this is about fatigue failure.